Welcome, everybody. Thanks very much for taking a seat, coming here so we can have a nice talk with our guests. The Paris Air Lab is really the place to be if you want to learn more about the incredible revolution that is taking place at the moment, a revolution that can be summarized in one word: decarbonization. And the exhibition here will tell you a lot about it. You can learn a lot about it here with this exhibition. But the Paris Air Lab is also a place where key players make important speeches on strategic and technical issues going on in the air transport domain. So we are absolutely delighted to have here at Paris Air Lab and to be able to welcome two very important decision makers from across the pond. Robert Pearce from NASA is here and he will be talking in about half an hour. And for now, we're very happy to welcome the Chief Sustainability Officer of the BOEING company. This is Raymond. Would you like to come, Chris?
Thank you, Paul. Thank you very much. Well, thank you, everyone. It's a pleasure to be here. Thank you for having Boeing, and to the commissioner and all the organizers of the Paris Air Forum. Thank you, Anne, for having us. It's great to be here. And thank you all for taking time out of your day to talk a little bit about sustainable aerospace. And what better place to talk about it than here in the Paris Air Lab, where all around us are exhibits about what the future holds for our industry as we seek to decarbonize this industry. We talk about sustainable aerospace as sustainable aerospace together. Can you hear it? Sure. Yeah? We talk about sustainable aerospace together. Closer? Okay. All right. We talk about sustainable aerospace together because in our view, we've solved a lot of hard problems in aviation, but this hard problem is going to take a collaboration between aviation, the energy industry, the banking and the capital industry, and policymakers if we're going to solve these things and scale up the solutions that we're going to need. So I'll talk a little bit about that. You know, as we think about 2050, first of all, I would say, in my mind, and I've been in aerospace for 37 years, but in my mind, I think we're very fortunate as a big global industry. I think this industry is integral to modern life. I would show of hands, I won't ask you to do it, but if I asked you for a show of hands about who flew here today, and then if I asked you to keep your hands in the air if you carbon offset your own flight, or if you even know what your carbon emissions were for that flight, we might get a different set of hands in the air. But aviation is integral to modern life. It connects the world, it protects the world, it provides economic stimulus, economic development, trade. It draws science and technology and engineers and mathematics all to this industry to solve these problems. And it contributes to the global economy. If I was just to give you a few numbers, in 2019 to 2020, before the pandemic hit, aviation moved 4.5 billion people around the world. There's no doubt that part of that was connecting cultures like we're doing here today, letting people of different opinions or different nationalities talk to one another, solve problems, discuss things that we're opposed against each other on, discuss how we might move forward. And we look at the diplomacy that's going on in the world today, and aviation sits underneath of that. From an economic point of view, in that year, there were about $7 trillion in economic goods exchanged, and this industry is purported to provide about 88 million jobs, many of which people like me get to enjoy. As we move towards 2050, those numbers are going to grow. Just the passenger movements alone are projected to be 10 billion people by 2050. So if you think about what that's going to mean, our cities are going to be bigger. People are going to desire to move around in our cities and between our cities differently. Time is going to be a very important component to all of us. We all want to do things faster. We want to get there. We want to minimize those travel times. And we're going to continue to face climate-driven policy in aviation as well as we move towards 2050. But I think about the history of this industry, back to the 1950s when the 707 introduced jet transport to the world, or when in the late 1960s we took humanity to the moon. So this industry can solve hard problems. And I would almost argue that no other global industry has the bodies to have these discussions like aviation does. In 1944, the world was a challenging place. And a lot of governments came together, about 30 governments came together in Chicago, and that was the beginning of ICAO, the International Civil Aviation Organization. And that lets us get together as governments and talk about issues to keep aviation safe and sustainable and allow the freedom of the skies and allow the world to be connected. And we have another institution called IATA, the International Air Transport Association, which all of our airlines belong to. Over 300 of them belong to IATA. And IATA was formed in 1945. These were not easy things to do to bring our community together globally, but we did them. And that gives me great hope as we face into the problem that has to be solved now, which is that 2.5% of carbon emissions and equivalents that we provide to the planet in our industry to do what we do. And now our challenge that we have in this industry is really how do we preserve all those benefits and continue to enjoy all those benefits, but decouple the carbon emissions of our industry. But I'm hopeful because that challenge is drawing a lot to our industry. Venture capital, entrepreneurs, new engineers, new people trying to solve this big challenge that aviation has. So it's an exciting time in the industry, and I know our industry can solve it. But what's it going to take, to solve it? And at Boeing, we talk about this in terms of 4 big levers that it's going to take to solve it. First of all, many of you may know or not know, when an airline replaces their older airplanes with their newer airplanes, they are more fuel efficient. If they were not, they would not sell. And historically, we've done a very good job as an aviation industry having those airplanes be 15 to 25 to 30% better than whatever they replace. And if I could put that in a term, like a personal term for a moment, if you got in your automobile in, say, London, and you could drive straight across the Atlantic Ocean to New York, that might take you about 50 hours, 50 hours. You'd probably burn somewhere in the neighborhood of 530 liters of petrol to do that. If you get on a modern airplane, you're there in, 7 hours. You've probably burned for your individual seat somewhere in the neighborhood of 130 liters. So this industry has worked on fuel efficiency. It will continue to work on fuel efficiency. It competes on fuel efficiency. The second column will be the operational efficiencies. And the airlines work very hard to find these little things. And you think about single skies or air traffic management or optimal flight routing, all these things, these little things, they add up to important efficiency gains in our industry. 1%, 2%, 3%, 4% of fuel burn. And now, when people talk about those fuel efficiency gains, they don't talk about them anymore in percent of fuel saved. They talk about them in tons of carbon emission saved. Just look at the airline announcements that are made now, and you will often see the amount of tons of carbon that are going to be saved when these newer, more modern fuel-efficient airplanes replace what they had before. But in the third column, you'll see where a lot of the discussion and a lot of the exhibits in this hall are focused. It is the idea of what will be the energy carriers for our industry in the future. We've got 100 and some years of optimizing around jet fuel. It is a very efficient fuel and energy carrier for our industry and the complexities of our industry. But this is where we'll talk about sustainable aviation fuels. This is where we'll talk about electricity. This is where we'll talk about hydrogen. And one thing, when we consider these energy carriers, we have to take into account, and some of the displays in the room do, we have to look at the total life cycle of these energy carriers if we're going to fix the climate problem in the industry. We have to be concerned with where is that fuel produced? Where is it pulled out of the ground? What's used to make it? How much electricity does it take to make it? How much hydrogen does it take to make it? Is the hydrogen green? Is the electricity renewable? Almost all these things depend on renewable electricity and green hydrogen. The question is, how will aviation use it? So at Boeing, our view is it's going to take sustainable aviation fuel no matter what. We're doing the research on electric and on hydrogen, but it's going to take a lot of sustainable aviation fuel for this industry to get to net zero by 2050 in almost any scenario in our view. And we can talk about sustainable aviation fuel, but if you go back to the 2006 time period, our industry was asking, is this even possible? Can you fly an airplane on the kind of sustainable aviation fuels that are off here to my right? And everybody said, oh, I don't know if that can be done. What did this industry do? In 2008, Virgin Atlantic flew the first airplane on sustainable aviation fuel. And then we learned how to qualify those fuels. Now there's 7 different ways of making it that can be flown on airplanes. And in that qualification, we limit the blend of those to 50% jet fuel and 50% sustainable aviation fuel. But imagine the carbon emission savings we'd have if every airplane that took off was taking off with 50% sustainable aviation fuel. That is our good next step to reach. And you see nations around the world writing policy to try to encourage the scale up. You saw the French president on Friday, President Macron, made an investment in sustainable aviation fuel. I can tell you in my country, the United States, government policymakers are working very hard to try to grow that industry through tax incentives and encouraging innovation and the R&D grants that are needed to expand the ways that we can make fuel in the future. And just look, a year ago at the air show, just look at the number of fuel offtake agreements that airlines have made, the number of fuel producers that have said we're going to start making SAF, and the number of policies that have emerged in countries and states around the world. ICAO is very focused on it between now and the end of the year, and we'll talk about it at the climate conference in Dubai later in November. Sustainable aviation fuel is required no matter what. But we're also working on the electric and the hydrogen aspects, and I'll just point 2 pictures out to you in this diagram. The yellow airplane that you see is Whisk. It's an all-electric, all-autonomous airplane. I'd encourage you to go down to the booth and see it. You can talk to the team down there, but that airplane is with the FAA right now being proposed to be certified as an all-electric, autonomous airplane. We will learn a lot. That will be a difficult process, learning how to safely certify that airplane. Just below that, you see a large circular tank on the back of a truck that says oversized load. That was a composite hydrogen fuel tank, cryogenic fuel tank, meaning it could keep the hydrogen very cold. And that is about the size of a tank you would need to fly a regional jet on hydrogen. So we've got to solve these problems. We've got to continue to do the research and development around these things. But our view is we're going to need a lot of sustainable aviation fuel no matter what. You know, to explore these different scenarios, we invented a model. We're collaborating on this model with the University of Cambridge at the Whittle Lab, with MIT, with IATA that I mentioned earlier, and with Mr. Pearce's organization, NASA. And the idea is you don't have to believe our opinions of what will happen. You can explore your own scenario. If you think fleet renewal will go faster, you can do that. If you think operational efficiencies will be greater, you can do that. If you think there's going to be a lot more sustainable aviation fuel, you can do that. But what it will force you to do is decide how clean is your electricity and how green is your hydrogen, because that will make a big difference to whether we're actually reducing the carbon emissions of aviation. But this model, called the Climate Impact Model, is available to you. If you go to sustainabilitytogether.aero, sustainabilitytogether.aero, you can go play with it. And you'll see this screen. So on your left, you can take a little self-guided tutorial. You can learn about the tool, learn how to use it, and then start playing with it. In the middle column, you can explore the scenario I mentioned. 2019 to 2020, 32 million flights, almost 900 million tons of CO2 equivalents. But you can go start to pull those levers and decide, what do you believe is going to be possible in the future? And what's going to have the biggest impact the fastest on helping this industry get to net zero by 2050. So go check it out and go play with it. And then one last thing I'd point out to you. Just the other day, Scaling up sustainable aviation fuel. Scaling up sustainable aviation fuel is a difficult challenge. But these are all difficult challenges. Scaling up renewable electricity is a different challenge. Scaling up green hydrogen production, difficult challenge. The reason the aviation industry is focused on scaling up sustainable aviation fuel is we understand the implications on the airplane. We understand the implications on the airport. And we understand the implications on pipelines and the distribution infrastructure of fuels. And because we do, that is the solution that can help this industry the fastest. And this is a tool that is also available to you on sustainabilitytogether.aero that is going to track the announced production capacity of sustainable aviation fuel. And you can look at it by region of the world. You can look at it by the type of fuel that's going to be made. Those types are displayed on the table right over here, the different ways to make sustainable aviation fuel. But you can go check it out yourself. And we as an industry, working together with oil and gas companies, working together with entrepreneurial fuel breakers, working together with policymakers, and working together with the banking industry for the capital that's going to be required to scale this up. We have to keep track. And in a year from now and 2 years from now, people are going to ask, is sustainable aviation fuel scaling up around the world? And I believe that's why you see countries and nations and governments making investments in it and writing policy to build that industry up. And I suspect that's what the French president did on Friday. So anyway, that is the end of my prepared remarks. I guess I'll just leave you with, I think we'd all agree at the Paris Air Forum that aviation is integral to modern life. We all wouldn't be together if it wasn't for aviation. So it's integral to modern life. The industry is extremely focused. I've demonstrated just a little bit, and Bob will do a better job than I will. The industry is very focused on reducing the carbon emissions and the non-CO2 effects of aviation. This is a focused industry. And the industry has always competed on fuel efficiency. So when you have an industry that actually just wants to use less of it no matter what, and whatever we have to use, we want it to be sustainable going forward. And so if you've got any good ideas after you check out sustainabilitytogether.aero, send them in, play with it for a while, and help us make it better. And thank you for your interest in sustainable aviation.
Thanks very much, Mr. Raymond, for this very inspiring speech. We still have a bit of time for questions. If anyone would like to ask a question to Mr. Raymond, or maybe give an insight or testimony, maybe I'll ask the first question.
Or might need a break.
Oh, we have someone here who would like to ask a question. Here I come.
Hi.
Hello.
Amelia Gilchrist from Rolls-Royce.
Hi, Amelia.
One of the High Five ambassadors for clean aviation as well. I'd just like to ask about, so you mentioned the life cycle impact of sustainable aviation fuel and hydrogen and all the other options we have. What about the logistical challenges involved of creating supply chains that are reliable and sustainable throughout?
I agree, and I think that's why we have to look at the life cycle carbon emissions of any of these fuels, including the distribution. I know there's a model that's used in the United States, the Department of Energy GREET model, seeks to look at that whole value chain of fuels and put a carbon intensity score on it, and it includes distribution and logistics. And so I think the pipeline problem, or whether we're trucking fuel to different locations, has to be taken into account. And what I've seen is a lot of the big mature infrastructure of oil and gas, they have some of that today. Some of the newer companies like Sky Energy or Alder Fuels or people like that, they're citing their projects where they have some access to that distribution or pipelines. That's a very important consideration when they're creating their facilities to do that. And then I think the reality is we're going to need a global book and claim system or a global registry, because Mother Earth won't care where we're using the sustainable aviation fuel. And the chances are we're not going to scale it up everywhere in the world equally as fast. And nobody should be penalized for wanting to use it, and nobody should be incentivized to do a crazy thing with the distribution of it just so they can say they're using it in some other location. So I think one of the challenges of our industry is to build a global registry so that somebody can buy the aviation fuel where it exists and then get credit for using it. Hope that answers your question, Amelia. Thanks.
Anyone else? Sure.
Thanks very much. Thank you for the presentation. It was very interesting. So I'm Jamie. I work for a UK-based company called Signal. We're part of your aerospace accelerated program. Yes. So thank you for that also. So from my side, because we work on behavior change and we're really interested in the human elements, I was wondering how you think we can address some of those human factors when it comes to the operational efficiency. Especially when we have so many stakeholders in aviation where the interests of one party don't necessarily align with the wider fuel efficiency and sustainability of the network.
I'll try to answer your question, Jamie. If I don't get it right, you tell me. But I think the human behavior as it relates to operational efficiencies, I mean, I don't know if this is where you're going with the question. If it's not, tell me. But I think when we can portray these operational efficiencies in terms like weight savings or fuel burn improvement on airplanes, that's the language of aviation. And so if any of these operational efficiencies can be portrayed that way, it's going to save carbon emissions. We were just having this discussion down in another hall about the importance of weight on an airplane. You know, every airplane wants to weigh less and go further on less fuel. And if we can do that in our operational efficiency gains, and you know, I don't think that's going to remove humans from the process if that's what we're getting at, but I do think those are going to always be important. And then I think in terms of the broader question about getting parties together, you know, that may or may not agree, I think the human behavior that I see coming up in our industry is all of us as the flying public. And will we accept an airline ticket that got more expensive because the airline's using sustainable aviation fuel? Or will we switch to a different airline? And that's a very important consideration on all of our behaviors in the industry, I think. And I give the airlines all the credit. They're doing what they can, I think, to educate their flying public about this. They're trying to give them different choices that are available today for carbon offsetting their flights or investing in a sustainable fuel fund. Those could be controversial to some people. But I think it's the early signs of them trying to give us as consumers choice to live our values and fly. And I think that is going to be a very challenging sort of human behavior environment as we go forward to educate people about how they can have the benefits of flying, but we also have to work on decoupling that from the carbon emissions of flying. And that's going to be the human behavior challenge we're going to have to work on. Thanks.
Mr. Raymond, tell me, decarbonizing air transport comes at a price, right? It's very expensive. Like, for instance, if you want to use SAF, sustainable aviation fuels, you know, they are about 3 times or 8 times more expensive than kerosene, right? So it means that the airlines which will use these SAFs will have to pay a price for that. Sure. So don't you need, and it's a problem within the competition between all airlines, right? So don't you think that rules and regulations and mandates should be harmonized at the world level? So everyone, you know, there's a challenge that's, you know, the same for everyone?
Sure. I mean, that might be ideal. I'm not sure that's the world we live in, frankly, but that might be ideal if we could harmonize that. But what I do see going on is people trying to incentivize the capacity. And that's one reason we built that model, so we could assess as capacity additions happen. So in some places, the policy is seeking to incentivize the capital to flow into the capacity. In other places, the mandates are being put on for the use. It's not my job to say which form of policy is the best. All I would say is, where we're going to use mandates, we have to pair them with the incentives to also keep those funds in the sector to scale up the production of the state aviation fuel. That's going to be very important no matter which policy lever that's turned. And, you know, as I mentioned, expensive. And I think Cheers. Thank you. I think that's what gets back to this question that was asked here about the fact that the fuel will be more expensive in the beginning. Jet fuel is not a stable price. Jet fuel is fairly volatile too. Sustainable aviation fuels right now would be a premium. I think as Willie Walsh from IATA said, though, every drop we could make last year, the industry bought. And so we will face a bumpy ride as we harmonize supply and demand and pricing. But I think the direction of travel is clear. The airline industry understands it and is supporting it and is lining up access to that fuel. And that's why every drop of it was bought.
Anyone else, maybe? So maybe one last question. If you look at airplanes, right, the last airplanes that have been flying for the 20 or 30 last years, for non-specialists, they kind of all look alike, right? They all have this round nose, these 40-meter wide wings, that type of thing. Do you have the feeling that the shape, the airplane shape, is going to be a lot is going to change a lot in the future? Like we are going to have open rotors, longer wings, maybe new propulsion systems. Maybe we'll have to change the whole shape of airplanes in the future.
Sure. I mean, I'll just start with the fact that you don't see a lot of the innovations sometimes that go into the airplanes. And I'll just point out one of our airplanes. Bob will have much more information on this, but I often hear this idea that there's not enough innovation until an airplane looks radically different. Number one, we wouldn't have gotten that fuel efficiency improvement that I mentioned earlier if there wasn't a lot of innovation. You think about the materials that are used to make airplanes. In our case, the 787 becoming a carbon fiber airplane. Or what you don't see is the electrical system of the airplane. The airplane has 1.5 megawatts of electrical power on the airplane with battery power. And that was a challenge in the development of the program. But now it changed the electric architecture of the airplane, took pressure off the engines so the engines could have more fuel efficiency and more range combined with the materials and the aerodynamic improvements. So I think you're already starting to see our industry explore every single aspect of efficiency. Part of that will be weight and materials. Part of that will be the aerodynamic shape of airplanes or things like the transonic truss-braced wing. And we'll also look for those little operational efficiencies. That's what the industry does. It explores these things. And I would just predict for all of us, including in this hall, that you're going to see over the next 5 to 10 years, you're going to see amazing announcements come out of this industry. You're going to see prototypes. You're going to see tests. You're going to see first flights. You're going to see new fuels used on airplanes. And there will be a press announcement every single day as the industry innovates its way forward on this topic. And that's what we do. We have to determine if things are technically possible, and we prototype and test and fly things to do that. But it will go nowhere in our industry unless it's safely certifiable. And it shouldn't go anywhere in our industry unless it's safely certifiable. So we'll work on the technically possible. There's innovation in this room and beyond on that. We're going to work on what can be safely certifiable. Then we'll have to solve all the economic questions like SAF costs more than jet fuel. And then we'll have to decide, did all of that work actually have the climate impact we wanted it to have in the first place? Because that is why we're doing it all.
Mr. Raymond, you have to come more and visit us here at the Paris Air Lab, all of Boeing. You're welcome here.
All right. Thank you, Paul. Thank you for moderating.
Sure, thanks very much.
Thank you.
Thank you very much, Mr. Raymond, again. And now we have another speaker. Here he is, standing. Mr. Pearce, don't go away. We need you. Mr. Pearce, Robert Pearce, is the Associate Administrator of the ARMD. The ARMD is the Aeronautics Research Mission Directorate at NASA. So, Mr. Pearce from NASA, please come on stage. Can we have a big round of applause for Mr. Pearce, please? He will tell us about sustainability as well. If you need, you have slides, right?
I do have some slides.
Okay.
And there's a video as well.
You push it here to move it on, okay?
Okay, good. Good morning, everybody. It is great to be here, and thank you for the organizers of the Pearce Air Lab for having this event and for inviting NASA to be a part of this. Actually, Chris Raymond, my colleague at Boeing, did a great job setting a stage for how we get to sustainability, and I can talk about how NASA is supporting that. And I've got a video and I got some slides to do just that. Closer? Thank you. Okay, sorry. I got a video and some slides to do just that. But one of the things I would just point out is Chris talked about there's 4 sort of pathways to sustainability. One was around fleet renewal, around operational efficiency, around sustainable fuels, renewable fuels, and around technology. And NASA has contributes to all of those, and that might seem a little unusual, right? But I'll just point out that NASA was formed and it was established in 1958, but the first day in NASA had been around since 1915. We've been around since the beginning of aviation, and we've been a contributor to technology and to advancements in aviation ever since then. And so all the vehicles that are, and the new airlines, the new aircraft that are coming into the fleets, all carry NASA technology. So even that fleet renewal carries NASA technology with it. Up here. All right, I'm going to get this right eventually. You got to hold the mic just right in order for this to work. Okay, so apologize for that. So every vehicle coming into the fleet today carries NASA technology on it, and some of them are very visible, and some are sort of kind of disappear into the background because of the methodologies and new materials, new aerodynamics, and so forth that maybe aren't immediately obvious to begin with, but are there and contribute to fuel efficiency. So let me start, and I think I've got a video here. Is there a video that's to tee up? I'll give it a second. If the video comes, the video is way better than I am, so we'll let that go. But if not, then I'll just launch in and give the talk. No video. Okay, so sorry about that. You're missing a great video, but I'll launch in. So this represents a vision for the future of aviation. So I want to start sort of really broad-based and talk about what we see for the future. And some things up here might look a little unusual if we're talking about sustainability, but I'm going to try to talk about why we think we need to look at a very bold vision for the future of aviation, and why I think all of it can contribute to sustainability in the long run. So up on the top here, you see, the main focus, what folks really think about is really at that top, is right, those ultra efficient airliners. Let's get airliners that are much more highly efficient than today. And so that's a big focus for NASA technology. We're looking at technologies that can contribute to up to 30% more efficient aircraft. And we'll talk a little bit about how we do that. But 30% more efficiency is a big number in aviation. It doesn't come easily. It comes with a lot of hard work and a lot of R&D to develop technology. And of course in there as well is the fuels that power those aircraft. Try to get to low emission from a life cycle perspective. Those renewable, those sustainable aviation fuels. On the right-hand side at the top, you see the airspace. Again, Chris talked about the fact that we need to have a very efficient airspace. And while, the numbers don't seem very big, maybe a couple percent, 3% of efficiency, you think about having those very efficient aircraft that are operating. You want them to operate absolutely as efficiently as possible. So we want the airspace to be as absolutely efficient as possible. And so we work with the FAA and others on these tools that enable optimal trajectories to fly throughout the system. And so that's really important. And as Chris said, safety is really critical to all this. None of these technologies will get into the system if they're not absolutely safe. And you think about how safe aviation is today. So maintaining that safety is a really challenging problem. And we have to go to a system that is highly prognostic. So as we introduce new technologies, which naturally introduce risk and hazard into the system, we need to be able to discover risks. We need to be able to discover hazards before they become incidents, before they become accidents, and correct those, mitigate those things. So that's exactly the thing we're focused on. And so maybe safety doesn't seem like it's integral to sustainability, but it absolutely is, because we need that to get to that prognostic system so that we can introduce technologies as rapidly as possible. And then the bottom are new forms of mobility. And the one that's probably most controversial is down here in the lower left. Can we get to higher speeds, right? So we go to higher speed, we go to supersonic, we burn more fuel. So how is that sustainable? And the answer right now is it's not a sustainable, we don't have supersonics. Some don't want supersonics to ever exist. It's hard to see how we get to sustainability. But from a research perspective, from a NASA perspective, we're here to solve hard problems. And so there are 4 key issues associated with supersonics. One is the overland noise, right? The sonic boom. Can we lower that to a sonic thump? And we're working on that right now. High altitude emissions is another issue. Landing and takeoff noise, and then overall efficiency of the aircraft and the availability of sustainable fuels to power it. Those are all challenges. Again, NASA is here to solve hard problems, and that's where we're going to tackle these problems one after another. And if we're successful, we hope to see the introduction of sustainable supersonic aircraft. If we're not successful in overcoming these problems, we won't see that innovation, but that's the nature of research. And on the lower right-hand side, one of the areas that Chris mentioned was WISC. WISC is one of those companies that's developing an eVTOL and trying to create an advanced air mobility system or urban air mobility system. The ability to operate at short distance, much more efficiently, much more rapidly, and so forth, do it with all electric propulsion systems and so forth. So NASA is integral to that. We have our own research that's developed distributed electric propulsion, and we're testing that out. But some of the big things we're doing there is really more on the operational side. How do you have an air traffic management system that enables that kind of advanced air mobility? How do you have the safety management systems, those prognostic safety management systems that enable that advanced air mobility system? And so how do we look at the life cycle of advanced air mobility, how we introduce it safely, how we introduce it in a sustainable way? Those are some of the challenges we're focused on. For the rest of the pitch, I'm going to really focus on what we're doing in our sort of core part of our portfolio, which is really around sustainability. And so in the US, we've got a policy just like the rest of the world, and that is to address the climate crisis through three major pathways. The goal is to get to net zero emissions by mid-century. It's the same as ICAO, it's the same as most of the world. That's the goal. How do we get there? So these are the major pathways. Again, there's no surprise here. Technology, we have a primary role in technology, aircraft technology and otherwise. We do have a supporting role in sustainable aviation fuels. So the kind of things we do there, we characterize these fuels for operation. We also do things like to optimize combustor technology. So where it burns in the engine, those combustors, to optimize those for the use of sustainable aviation fuels. And then in operations and air traffic management, some folks don't know this, but within the US, NASA is actually the research arm for the future of air traffic management. We partner closely with the Federal Aviation Administration in doing that. But in the US, the next gen air traffic management system, those technologies for trajectory management, were all developed at NASA labs and then transferred to FAA for operation. And we're going to continue to do that to make sure that we get to absolutely the most optimal trajectories that can be flown. So what are we doing on the vehicle side? So for the next generation, we've been working for the last decade or 50, this is not new, right? We've been working for a long time on what potential technologies could really have a large impact on the efficiency of future aircraft, future airlines. And so what you see here is the concept, the transonic truss brace wing. It's actually quite simple. It's basically long, slender wings. So higher aspect ratio wings, which just have less drag, less what's called induced drag, so less drag due to lift. So higher LOD, which means It's a more efficient aerodynamics, more efficient wings, and so less fuel burn. But you can see to get to those really long, slender wings, we had to do creative things structurally. So you see that truss there that helps support the wings. Because we need to do this, you need to have those long, slender wings without a weight penalty. We don't want to add weight to the aircraft, because if we add weight, then we're going to increase the amount of fuel that's required. So how do we get those wings and not add any weight? That's the challenge. So we're actually going to go, we have announced, and we have a partnership with Boeing, as a matter of fact, to do this. We've announced that this is now an experimental aircraft that we're going to build. It's the X-66 in the United States. And we're actually going to build a full-scale version of this as an experimental vehicle to prove out that these transonic truss-braced wings really deliver the benefits that are predicted. So about 10% improvement in efficiency through those wings. But that's not enough. We need the propulsion system as a part of that efficiency, those efficiency gains, those efficiency equation. And so we're working on better improvements in the turbine engine, the ability to convert the energy into useful work, into propulsion to move the aircraft. So we're looking at the thermal efficiency of the engine. How do you convert, again, the energy into work? And do that and try to shrink the core of the engine. If we shrink the core, that means we can increase the bypass ratio of that big fan that sits out in front. And that big fan that sits out in front is where you get most of your propulsion and the efficiency that you get. So the larger that is, the more efficient your propulsion can be. So we get both thermal and propulsive efficiency out of the work we're doing there. We're also going to try to get to a hybrid system. So let's add electric power to the turbine. And so that's a first increment of trying to get to a hybridized large aircraft. And so we've got experiments that are going to get to flight here in just a couple of years to demonstrate megawatt powertrains at altitude. So we've got a couple of partners there, General Electric being one, magniX being another, where we'll actually take megawatt powertrains and we'll flight demonstrate them, demonstrate the efficiency and demonstrate the safety and the operability of these large systems at very high altitude. And if we can do that and we can combine it with the turbine, between the improvements in turbine efficiency and the improvements that comes from the electrification, we get another 15 or 20% of efficiency improvements. So now we're up at that 30% range. In addition, these aircraft want to be composite to get the lightweight, but we also want to be able to produce them at higher rates. We want to be able to produce these aircraft more rapidly and economically. And so we're actually working on how do we improve the speed and efficiency with which we produce composite structures. And so that's another major project. And so these are all the areas, these are all the ways in which we're looking at improving that next generation, trying to get upwards of 30% more efficiency out of the vehicle itself. And again, you know, that the issues around sustainable aviation fuels, those are very precious. That's a very precious source of energy. So you want to, again, burn that as efficiently, you know, have the most efficient aircraft using that possible. So these efficiencies are really critical. And so just some dates, we're going to begin flight demonstrations on the X-66, on this transonic truss-braced wing in 2028. We're going to complete ground tests of some of the other components around that transonic truss-braced wing in 2026. We'll do some capstone demos of the ability to produce both fuselage sections and wing sections at very high rate by 2027. A high-efficiency engine core demo in 2027 again. And then flight tests will begin on the electrified aircraft propulsion in 2025. So these are all coming in the next several years. Again, as Chris said, there's a lot of announcements coming because it's of the collective investments we're all making. And so NASA will be contributing to that. All of these are in partnership with industry, cost-sharing partnerships with industry, because we want this to make sure there's an economic pull to this as well as a technology push. So this is all very exciting, and it'll all lead to real benefits in the system. We're also looking at sustainable aviation fuels. Like I said, we do a lot of characterization. One of the greenhouse gas issues that we have within aviation, of course, is the formation of contrails as a potential contributor to global climate change. There's a lot of uncertainty associated with contrails and how much they contribute. So one of the things NASA wants to do is to study this problem and reduce the uncertainty so that if we if contrails is a big problem, then we can figure out what to do about them, how to avoid them. If they're not as large a problem, then we can focus in other areas. So we're studying this problem, and so we did a ground test. This is of a CFM LEAP engine, and this is a NASA sampling probe, so we can actually look at the effluent, so we can see what's being produced, the emissions that are being produced, and then we can start to put those into models. And we are planning some flight tests where we'll have an aircraft actually burning sustainable aviation fuels, and we'll have we have a special aircraft. It's a DC-8, it's an old airplane, but it's loaded with instrumentation, so we can basically sense what's happening behind that aircraft, pull all that information in, and get better atmospheric models. And so we'll be doing that work as well. And then air traffic management, like I said, optimal trajectories. And so we're doing these integrated trajectories to get a lot of environmental benefit. What we're really, the end state here is automatic negotiation between the flight deck and the air traffic control tower to make sure that you're getting, every aircraft can get the optimal trajectory during every phase of flight. So that's the ultimate vision that we're working towards. Finally, I just want to talk about, that's what we know, what we're doing today, right? But there's more to be discovered. There's more to learn. And so we push our researchers every day. We push our universities every day to think of new ideas for the future and new ways we can think about sustainability and other innovation in aviation. And so we've got a number of projects that do just that. And I'll talk about one on one we're doing on wildfire to improve aviation operations with wildfire management. It's a huge issue in the United States, and it's being made worse by climate change. And so we're trying to heavily automate that part of the ability to fight fires with aviation systems. And so we have a start at that using drones to operate in the wildfire area, so it can do surveillance, it can set backfires and so forth that helps actually control the fire. We have a large investment in university innovation, doing everything from hydrogen to hydrogen propulsion, ammonia-based propulsion, other forms of energy and propulsion, as well as other innovation, but trying to get them to think even further, get way out in front and imagine what could be. And then we've got some internally developing some really amazing new technologies. What's pictured there is a new material called GRX 810, off the charts in terms of an alloy that operates at very high temperatures and is extremely durable. That again, that kind of alloy can improve jet engines to improve the efficiencies. And so these are some of the, I'll go through this rather quickly, but I mentioned this. These are some of the universities that we've got working on some of the zero emissions ideas that they've come forward with. So you can see everything from superconducting electric drivetrains, hydrogen, I said ammonia, and other ideas. And so I'll stop there, and hopefully there's a little bit of time for questions. But please follow us. We're putting out stuff every day about the advancements we're making, the excitement we have, and I hope all of you will join us in this path forward. So thank you so much.
Thanks very much, Robert Pearce, for this speech and this insight into the innovation at NASA. Would anyone like to make a dialogue with Mr. Pearce? I can get the microphone to you if you wish. Otherwise, maybe I'll ask you a few questions on my behalf. Yes, there's a challenge to be, which is the decarbonization challenge at the moment. And at OACI, ICAO, many actors at the air transport domain decided that by 2050, we should reach this zero carbon emissions air transport system. How confident are you that this objective, which is very ambitious, can be met?
So I think it all hinges on the availability of sustainable aviation fuels, as was discussed earlier. And just as to get the magnitude...
A lot of it really relies on these fuels, right?
Yeah. ultimately, you can't efficiency your way to the future. You've got to have a fuel that gets the carbon out. To give you a sense of the magnitude, for U.S. operations by 2050, I can't get this thing close enough, right? Yes. By 2050, in U.S. operations, that's 35 billion gallons a year that will be required. A couple of 100 million gallons are produced a year now. So the challenge is, how do we scale? How do we scale up to those levels? And so, as Chris said, there are policies in the U.S. to subsidize and incentivize the production and the purchase of sustainable aviation fuels, because you got to get past that tipping point, right, where you get economies of scale, where the price starts to come down and the demand starts to go up. So that's the real issue. And I think there's issues on, it's not just an aviation problem. If the ground sector becomes more highly electric, like in the US, we produce a lot of corn-based ethanol. All of that feedstock could go towards sustainable aviation fuels. So there's a lot of work to be done, and there's a lot of policy to help incentivize that transition.
Let's see if I get it right. How's that?
I can hear you.
Okay, good stuff. I'm Howard Slutskin with the Air Current, Robert. Nice to chat with you. One question. We all need fuel for our aircraft to fly, but we also need money to make sure the programs move along. Are you at the point for the X-66 that the first tranche of funding that you're getting will take the program through the phase 1 completion, and will you have enough to keep going past that?
So the way, I'm not sure how many people are interested, but the way we get funded is on an annual appropriation through Congress. And so, we can't start a program until we get our first tranche of funds. And so we do have that, and we've signed an agreement with Boeing to do this. We will put in $425 million US dollars, and Boeing is putting in $725 million US dollars. So it's a very large and a very very important cost-sharing partnership that we've developed. But those funds we're working. The Boeing team, the NASA team is working right now on the design of that vehicle, and Boeing, in fact, has we're taking an MD 90 donor airplane as kind of the fuselage. So we're working, we're going.
How far?
Oh, from there. That aircraft, once we do the basic flight test of the transonic truss brace wing, there could be opportunity to do additional technology development, additional work with that aircraft. We haven't made those decisions yet, but we could certainly see that happening. There could be maybe additional propulsion work we might do, maybe additional aerodynamic work we might do, maybe some materials and so forth. So there are definitely ideas for what we could do once we get that the basic flight test of that transonic truss wing done.
Mr. Pearce, tell me, of course, we've been speaking about CO2 emissions, which have an impact on climate change, of course, but there are also, air transport airplanes have also non-CO2 effects.
Correct.
On climate change. Do you address that as well?
Yeah, so as I was mentioning, I think the biggest amongst those is the contrails, the formation of contrails, those white, contrails you see behind an airplane. And what happens is they induce cloudiness. They induce a layer of cirrus clouds that can hold heat in and form as a source of warming. There's a lot of uncertainty around that.
Do they have positive or negative effects on climate?
They can have both,
right?
They can have
Okay.
both. Yeah, so during the day, that cirrus cloud layer could actually reflect sunlight and be a little cooling. At night, they can be an insulator layer and hold warming in. Right now, the estimates is that they are a net warming. But when and where it's actually warming versus when and where it might be cooling, there's a lot of uncertainty. That's what we have to decide on, because there are techniques that would allow us to avoid contrails, but we might actually burn a little more fuel to do those techniques so we could produce more carbon in reducing the contrails. Well, carbon stays around for hundreds of years. Contrails stay around for hours, maybe a day. So that's a very, you have to get what the equivalent, climate impact would be from a contrail versus CO2 emissions, so you can intelligently make that trade. You don't want to do something that would make it worse, right? So that's why we have to have better scientific understanding of the contrail formation and the aviation-induced cloudiness that results from it, and then the impact on the climate.
We have time for one last question. So if anyone would like to speak with Mr. Pearce, so the last question will be mine, Mr. Pearce. You told us about air traffic management. So NASA is involved into air traffic management and innovation in this domain. What do you do there? What's possible to do in order to reduce CO2 emissions, for instance?
Yeah, so you can think about it. Ideally, as an aircraft, you would have an optimal climb. You would climb for the least fuel. You would fly at your optimal altitude for most efficiently least fuel, and then you would descend. So if you have one airplane, that's really easy. When you have a lot of airplanes, then there's conflicts. When there's weather, there's conflict. Where there's winds and so forth. And so what we do is look at how you create algorithms, to create these algorithms to actually take into account traffic, weather, winds, and so forth, to come as close as possible to everybody being able to fly their optimal trajectory. Now, it's not possible for everyone to do it, but we get as close as possible, and then we can, and the algorithms will sort out what that optimal actually, that close to optimal actually looks like.
So does that mean that in the future, airplanes will have to cooperate and make sure that they all have optimized flight path?
Yeah, so that's what will happen when we start to automatically link the flight deck to the air traffic control centers and have automatic negotiation so that each aircraft is put on the most optimal trajectory possible. So yes.
So NASA is about space and NASA is about aeronautics, of course.
Correct.
Thank you very much.
First day in NASA.
Exactly. Thanks very much, Mr. Pearce. It was a pleasure to meet you.
Thank you.
Please come back and meet us again.
Yes, thank you.
Mr. Pearce. Okay, we are not over yet. We have an event now, which is an event organized by the International Forum for Aviation Research, which is going to host the Early Career Network Challenge. Is Mr. Joachim Södrich here? Here he is. He's the founder of IFAR. Here's the microphones.
Well, thank you very much for the introduction. And Bob?
Can we have a big round of applause for Mr. Södrich, please?
Oh, okay, thanks. Very kind. Bob, if you care, why don't you sit down? Because you're part of the club. So Bob just presented the views and the exciting technologies of NASA and the vision for the future. And now ask yourself, what if we look at a more global point of view? What if we collect other research establishments? What if we have 33 researchers, young researchers, coming from 18 nations? And what if they start to design their own aircraft? And all this we would like to discuss in the next half an hour. And first of all, I invite the chairman of IFAR. Sorry, I call it IFAR, but that's a little personal thing, right? Of IFAR, Ibrahim Emer. He is, please come, he is the vice president of the Transport and Manufacturing Division of Canadian NRC. And he will talk about, first of all, what is IFAR?
Does he need this?
He needs it, definitely. And the microphone. Oh, do you have one there?
I'll use this one. Can you hear me? It's a bit noisy in the back. Well, thank you very much, Joe, and thanks for the opportunity to tell you about IFAR, which is the International Forum for Aviation Research. That's kind of started with the gentleman right on the right-hand side there, on the left-hand side, Joe Zudrich, when he was, I think you were heading up DLR Aeronautics. So I've got the big pleasure of introducing IFAR here in this forum, which hopefully will lead us to the next part of the discussion, which is all about the youngsters, really, the future. So what is IFAR? About a little more than 10 years ago, organizations such as NASA or DLR or my own organizations got together and understood maybe we should put in, it's moving too fast. We should put in, we just talked about sustainment and environmental challenges. These things don't know borders. So we had to kind of have collectively address this as an international fashion. So it started out as, what's going on here? It just walks by itself. Let's stay here. Yeah, it has a life of its own. Okay, maybe it's a clue for me to keep moving fast, and I'll do my best to kind of catch up with it. So it started out as a group of 10 organizations around the world. About a little over 10 years ago, they got together and formed the IFAR. Since then, we are now 27 countries strong. In fact, the latest one being Singapore, an organization from Singapore named ESTAR, which is a similar organization, similar mandate as most of us have, most of the members have. It just shows you that IFAR is a growing organization in a direction where we bring in players from emerging areas as well. This is quite funny. Let's go to what we do with an IFAR. We essentially have got 4 major activities. The first one being we get together every year, address these big challenging questions together in a summit. We discuss what our plans are. We discuss what areas of collaboration or partnership that we need to put together. The second one will be, IFAR is an organization that does work together. It's not just a conference or a summit where we share results alone. We need to engage our researchers going forward throughout the year to address some of these specific challenges that we found some alignment on. And we have 10 working groups that covers areas such as urban air mobility, the challenges of urban air mobility, for example. In one of the presentations that Bob just showed you, it's a major challenge, or even in sustainable aviation. So there is a list of working groups that we engage them throughout the year, and they work together, they deliver results, they actually work on projects together. And the third one is really the future of aviation. We need to bring in talent into our industry. There is a shortage of talent going forward because not only the problems are challenging, but also we have an industry that continues to grow, and we need to excite the youngsters in particular to come to our industry in a way and provide them a platform to develop that relationship and collaboration right early in their career. And that's probably the topic that actually we will discuss right after. And lastly, we are an international organization, so we are very cooperative with other international organizations, and we form alliances. And in this case, the International Congress for Aeronautical Sciences is one of our partners. And much more recently, we have established a very good interaction with ICAO, which is the International Council for Aviation, International Organization for Aviation. And maybe just to give you a bit of a sample, why is IFAR unique from any other organizations? I would say we're publicly funded organizations from these 27 countries with about 40,000 researchers, if you add them up all together. We have a unique space that we fill in between what universities do and what industry does. And all of these big challenges that you've heard on sustainability has climate impact, it has safety impact. We need to address it in a global way, much more than at a scale we can actually demonstrate the technology to a deployable state. And we are very unique in that sense, and that's where we form that organization. And maybe a little word about ICAO. I think we started this journey about 2 years ago, and really the alignment of what IFAR does and what ICAO does become apparent right away. And since then, we were able to actually put together a joint task force that look at a specific topic, which is urban air mobility. How do you make urban air mobility a reality in an international fashion? It was a wonderful relationship, if you will, just right from the start, to a point where we were able to engage, a select group of experts. There's about 80 researchers that participated in this joint task force from 17 different countries, and the actual report itself that came out is not just a collection, the collective view of the 17 organization, but it represents the entire IFAR membership, which is the 27 organizations that I just mentioned. And this is really, really valuable for ICAO in order to put these forward-looking regulations or international regulation in place. And I had the pleasure of actually passing that on with my colleague, who is my co-chair from ONERA, Bruno, last April at the ICAO headquarters, that final report. And I think we do see much more work in terms of bringing in the capability, the collective capability of our organizations to support international aviation. Let me see if I have covered all. The slide was doing its own. It just talks a little bit about what that assessment involved, anywhere from what's industry's capability in urban mobility, looking at all the technology and operational priorities as well. I think there was another chart maybe that you saw throughout, which I just want to touch, which is when we do, Bob just talked about what we do on sustainable aviation. In fact, what are the non-CO2 effects that we have to do a campaign, an international campaign, to collectively putting our capabilities together to do a real experimental measurement of emissions for where we burn biofuels or sustainable aviation fuel, for example. Each of our organizations do our own activities, but we also collectively bring ourselves to do something like that. In fact, we've done that emission measurement at altitude together, where there is JAXA, you can see, and DLR and NASA, as well as my own organization, who participated in order to actually bring that data together for international good. Maybe just to wrap it up, I would say the most exciting part is actually bringing in the young talent into the future, ensuring that I think this sort of collaboration continues into the future. And with that, maybe I'll just leave this to you to the next part of the presentation. Thank you.
Okay, thank you very much, Ibrahim. And now he already mentioned that. We come to the exciting part. These are the big bosses here on stage, but now we come to the ECN network, our early career network. And as I explained earlier, we have these 33 people here. And I also thank the president of ONERA, Bruno, to make it happen, and also to make this happen in order to show you what we can do in this international group and how eager and enthusiastic these young people are working together, not only during work, but also playing in the evening basketball. I saw that yesterday evening, so believe me. So can I invite, in order to explain us what this is all about, Prajwal Prakasha Shiva Prakasha, sorry, the other way around. He is head of the group at the German Aerospace Center, leading the aircraft system design and assessment. And this is what it's all about. Prajwal.
Thank you so much, Joe. Thanks, everyone. So, as Joe mentioned, and also Ibrahim and Bob told about all the sustainable activities and the IFAR, it's a network of young researchers. And as you could see, all the fun faces, this is 2019 versions. So we meet every year. And then now we will see what we do for the future. As you all know, aviation is a big challenge, and collaboration is a way to go to tackle this challenge. So what are the goals of our EFAR X challenge? X means exploratory, and it's like NASA and other X planes. So we have X challenge because it's exploration and a lot of learning. So the core values of EFAR ECN is networking, education, and collaborative learning, and also implementation in future projects like it is mentioned in the screen. So what we do in the ECN conference, every year we all meet, and it's not just like a conference listening to presentation. So it is a function of education, communication, networking, and collaboration. And more the number of organization, then there is a factor. It's into the number of organization. So we have several activities. So we have X Challenge. We learn about soft skill from all the expertise and mentors we have here. And IVX is a virtual exchange. So NASA and NRC organizes this heavily. And there is career advice and tech tours. Like we have seen, all of us are in Paris Air Show and cultural exchange. So this is about 26 organizations. And there is also different ethnicity involved. So there are about 30 cultures coming together. So it's a really, really big eye-opening thing for all of us. And as you could see, it has been there in Russia, China, California, Daejeon, Moscow, Hamburg, and now it's in Paris in 2023. So the whole challenge is aviation is a very big challenge, and there are multiple domains involved. As you can see in this pretty and also complex picture, so there is so many domains involved, and it's multi-domain. It's not just multicultural, multiple country, also it's multiple domain coming together. As you could see in this version of challenge, so we had about 18 countries participating and across 9 time zones. Why I say 9 time zones is we had a lot of discussion online. So before coming to Paris Air Show, so we had about 20, 25 sessions. And then when we have a conference, it's also hard to organize. What is the best time? So you could follow it by football or other thing. Usually it's in European afternoon. So you get maximum audience. And also we need to be in almost working time. But thanks to sometimes if it's in afternoon in Europe, in NASA it's 5 a.m. West Coast, and in JAXA it's night 8 p.m. But young researchers were flexible and they collaborated over the 20 different tools, as you could see here. So how it all starts? So it all begins, we all come together online or virtual, and then everybody has domain. So everybody is thinking, I have this domain, I'm into structure, I'm into aerodynamics. How do I bring all these things together? They'll come with a lot of questions, and we want to see place for every one of them. Then we have a discussion. So we play with post-its and everything, and this is how collaboration starts. It starts with a quick and easy way, and then we have all the post-its and everything, and then we play. Then, like right now, our communication is in English, so we need to have a standard way to communicate. If I'm talking in Indian language, or if you're talking in French, it's hard to communicate. So in overall, to take up this sustainable aviation challenge, we need to have a same language where different tools communicate. So this is how we have a standard communication, started a DLR, but now it's an open source and everybody uses. So, and then we have to make all tools or domains speak the same language. And this is where everybody aligns their tools without sharing. And then, so there are many partners, as you could see in the screen. So they come with different domains, different expertise, and also not just this. So there are several other things like managing the whole event. There is also some management aspect. There is also some airline aspect. There is also some different system engineering aspects. So they have their knowledge, but they won't share the tool. So because it's a proprietary information, so they don't have to share their domain tools or something. So only they get an input file, as you could see, and then they run their analysis tool, and then they share. One with the results, so hopefully we go better and improve with the iteration, and then we have a better aircraft. Now we go towards the timeline, so how it all happened. So we met in January, and then we had series of online and virtual meetings, and then towards the end of the June, so right now we have the first workflow where we collaboratively bring many domains together. And this is across, as I said, about 18 countries, maybe 25 ethnicities, and several tools. So you will see slowly how it happens. Imagine it's like a symphony. There is a master of symphony integrator. So then the green dot is a bubble. Example, the integrator is DLR. And then he wants to ask Onera to run an aerodynamic analysis. Then he sends a request, and the request is sent. And then he runs his tool at his place in France, and then shares only the result, nothing else, and then communicate. Now we see by other young researchers how we do this. and they will come and present. So as you could see, different logos. There are different organizations involved. Nobody is sharing any proprietary information or any tools. It is just we take a EFAR research baseline, and then we run this aircraft. First, we start with ELOT. They design the thing, and this entire workflow is created by DLR. And then it goes to ONERA. They have a tool called FastOAD that will do the preliminary design of aircraft. And then we go to INCAS, and then SIA, then JAXA, and it follows. So just for your input, so we will have just 3 examples. So we'll have first SIA to come and present, and then later we will have JAXA, and then we'll also have NRC presenting this. So once we have this workflow running, then we make it together, and then we run multiple iteration towards this. So just to start, let's start with SIA. So, and then we have Anna here, and she will present how she brought in her tool to design the vehicle. Anna.
So it's this one. Hi, everyone. Oops, sorry. Hi, everyone. I'm Ana Silva. I'm from Portugal, and I work in a company called SEIA, which is a center of engineering and product development in Portugal. SEIA works mainly in 5 big areas. So we have automotive, mobility, space, ocean, and then the coolest department, which is mine, aeronautics. In Portugal, you can find us in 2 sites. So we have one in the north, in Matosinhos, where you can find colleagues of mine that work in all of these 5 different areas. And then we have a second site, more to the south, in Évora, where we are fully focused on aeronautics. So just to give you a quick overview, my department, aeronautics, was created in 2009 when we started working for Leonardo helicopters. And ever since, we have been a part of a vast number of their programs. A lot of these helicopters, you can actually see them today and this week in the Paris Air Show. And we have been working with them ever since. And we have many other partners, such as Dassault Aviation, and a huge one for us, Embraer, which speaks very closely to our heart. SEIA has actually dedicated over 690,000 engineering hours in this project. And you can actually see the very first aircraft that was acquired by our Portuguese Air Force in this show. So feel free to visit and take a photo. And then more recently, building upon all of this structural analysis knowledge that we were acquiring throughout the years, SEIA has launched their own aeronautics program. So our first fully developed program in-house, which is called Luge 222. So it's a small aircraft for passenger or cargo transport. And what did we bring for this year's FRX Challenge? So my colleague, Pedro Albuquerque, and I, we brought a tool, a structural analysis tool, that focused on the analysis of the structure of the wing. And so we actually created a larger tool that incorporates smaller tools. And so what do we take as inputs? We need geometrical inputs. And some of these, our colleagues from ONERA in France will be actually providing to us. So, for example, span, sweep, dihedral. And then we also need loads. And these will be inputted to us from our colleagues in ILOT from Poland. And so how does our tool work? In the beginning, we take all of these inputs, and then we use a very recent tool that we have that was actually developed during a master thesis by our colleague, André Pereira, which is an amazing tool. And it takes these inputs, and it generates, within seconds, a finite element model that we can run then in Nastran for a linear analysis to have some results of how our wing is behaving. After that, we can run a TCL program, so another one, that will use Altair Hyperview to post-process the results. And in this case, for this IFRX challenge, we focus on tension analysis, so how our wing will respond to the loads regarding tension, and we are outputting von Mises stress results. And after that, we have like a crucial checkpoint. So does for example, a rib component, does the von Mises stress allowable is higher than the material allowable? If no, great, we don't change anything, but normally it's not the case. So what we do is we increase its thickness, so the component thickness, by a certain ratio, and then we go back to the top. So it's an iterative process, and we run it as many times as we need to have all components with positive margins of safety. And so what we focus on outputting for this EFRX challenge are the thicknesses of the ribs, spars, and skins, so the thicknesses that we need to have, and then the wing structural mass, which will be used by our colleagues from A-Star in Singapore. So to give you a quick overview, our tool basically produces a thickness evolution, and we are outputting von Mises stress results, but we could easily be watching any other parameters. So we could be watching wing deformation, compression, buckling, etc. So it's quite a powerful tool. So if you see this is our baseline. So we get a wing structure, and we can have it change. So you can define where you want the ribs, how many spacing, how it's the outer shape of the wing, which is quite powerful because you can do small parametric studies that if we were to produce this model, finite element model, we would end up requiring a lot of man hours to actually produce it. And this tool generates it within seconds, and then we run the whole cycle that I explained, and we end up having the final structure with size thicknesses, so we can have a better idea of how much would the minimum range of thickness be to satisfy a certain requirement. And so I just finished. I got to the conclusion that I didn't really introduce myself of my background, I'm sorry, but I'm a mechanical engineer, and I focus on structural analysis, finite element modeling, and the development of auxiliary tools to post-process these finite element models. So thank you so much.
Oh, no, sorry. Sorry about that. Thank you very much, Anna. Ibrahim mentioned before, you know, we look for new talents. And I think it might be interesting, especially if you have kids and you want to get them into aeronautics. What was your motivation to go into aeronautics? And you seem to be very enthusiastic.
Yeah, I am. Actually, I don't have a very romantic story about how I got to aeronautics, but I always loved understanding how things work. And so when I was younger, I was like, okay, what should I do? Should I go to aeronautics engineering, civil engineering, naval architecture, or even mechanical engineering? And I ended up in mechanical engineering, which I'm very happy about it because it gives you a broader spectrum of things. And then I found out about the aeronautics world, and it's quite an amazing world, and things are never the same, and you're always and analyzing different things. And so that was my motivation. It's quite a passionate area.
Okay, thank you very much. And I hope that stimulated, I don't know who is not in aeronautics here, but at least those who would like to join the aviation. Thank you very much, Anna. Very kind. And the intention really was not only to show you our competent young ECNs, but also the people behind it a little bit. So we are not working with artificial intelligence, but with real people.
Thank you very much, Anna and Joe. So, as you see, so we have several organizations, and several of the young researchers are here. You could find them in this badge, and you can talk. And due to the time limitation, apologies that we could not have everybody come and present. It's just a glimpse of different continents getting involved. So we had Anna from Portugal. So as you can see in the slides here, so you start from vehicle, and then do a quick aircraft design by Onera, and then INCAS collaborating, and then SIA. So next, who we have is, we have Yosuke from JAXA. So he will tell us what he did in terms of aerodynamic evaluation.
Thank you. So I'm Yosuke Sugioka from JAXA, Japan Aerospace Exploration Agency from Japan. And my expertise in the aerodynamics, especially for the wind tunnel testing and aerodynamic measurement technologies. So let me introduce the JAXA's future vision firstly. So JAXA is a Japanese public research organization specializing in the aerospace R&D. So the total employees of the JAXA is about 1,600, and there are 170 researchers in the aeronautic institutes. So the JAXA created the future vision and during the pandemic of the COVID-19. So the name is environment people-friendly, sustainable society utilizing by aviation. So the vision keyword is sustainability in accordance with the Sixth Science, Technology, and Innovation Basic Plan from the Japanese Credit Office and well-known SDGs by United Nations. So this future vision is categorized into 3 parts. The first is transport, the second is aviation integration, and the third is industry. The transport part category is to develop the sustainable air transport with environmental compatibility and safety and efficiency. The second part, aviation integration, is to contribute to the sustainable society by future air mobility, airborne platform, and disaster response. The third is the industry. This is made to transition to the sustainable aviation industry in manufacturing, operations, and maintenance, repair, and overhaul. So we had a project to achieve this future vision, and we do not have time enough to present our several projects in here, but please let me know the future vision of the JAXA. So I'm a specialist in the aerodynamics. As you know, the aerodynamics is the critical factor which decides the aircraft performance. So we need to evaluate the aerodynamics first in the airplane design process. So for example, fuel consumption and the cruise condition is affected by the lift-drag ratio. And the aerodynamic loss predicted by some tools input values for the structure and the equipment design process. So this is an important point, I think. The improvement of the predictability of the aerodynamic performance is necessary in design phase of the future sustainable aircraft because the several drag count is very important for the reduce of the weight of the aircraft and the selected engine part. So we need to improve the predictability of the aerodynamics of the airplane. So as you know, of course, Wright brothers evaluate aerodynamics using the wind tunnel. Now we can use the good wind tunnel and the CFD prediction. So then we bring the 2 tools for the evaluation of the aerodynamics in this EFIX challenge. The first is a first aerodynamic routine, and the second is the R4-3D. So the faster is the unstructured CFD code developed by JAXA. So it can predict the aerodynamics around the aircraft fastly. The second is the R4-3D. This is the structured CFD code developed by JAXA, of course, and mainly for rotorcraft such as helicopter, drone, and eVTOL. So this is our position in the MDAX workflow here as the picture shown. So the input to our tool is from the Onera's first AD developed by Onera, and the input value is the reference area and length, required cruise Mach number, and wing geometry. In this challenge, we focus on the aerodynamics of the wing because of the limitation of the time and computational resources. So the output of our tool is input to the hop sum by link Ping University, flight dynamics by Inkers, and the stability and the control theory by Paris-Saclay University. So we give the aerodynamics performance mark, including the aerodynamic coefficient for each condition. So this is an overview what we do in the E5X challenge. So we extract the wing geometry from the CPAC's common language file from the developed the DLR, and we create a grid. We generate a grid for the CFD using our grid generation tool. And then we conduct a CFD using the R4-3D because of the grid generation is structured code is easier than the generation of the unstructured code. So then we get lift coefficient and drag coefficient. Then we have the output file in CSV, and then we input these values to the common language CPACs using our output wrapper. So then we contribute to the aerodynamic aircraft design by using our aerodynamics prediction tools. So this is our presentation. Thank you.
Thanks a lot. Thanks a lot. The challenge, as you can see, is these young researchers work on an interdisciplinary topic we have here. They bring in their expertise, their tools, and despite the fact that it's all based on physics, but there is still the cultural aspect, and again, 18 nations are working on that together. And my question is really, what did you study, and why did you study that?
Why did I study aerodynamics?
Oh, okay. Ah, yes, okay. No, I'm not surprised. And why?
So, firstly, I like aircraft with the beautiful shape by aerodynamics, decided by the aerodynamics. So I visited the Mitsubishi heavy industry when I was a university student, and I saw the main wing of the regional jet. It's gone, but so my eyes, so the beautiful wing caught my eyes. Then I want to try. So I want to contribute to the design of the beautiful wing using my specialties.
Okay. Well, thank you very much. You have lots of time now to see the beautiful wings on the air show. Thanks a lot.
Yeah, thank you.
Thank you, Yoshiko. So as you could see, one thing I would like to stress is that it doesn't mean that JAXA works only on aerodynamics, or NRC or SHIA works on structures and others. So there are also many organizations. So also we have an ability to swap this tool from JAXA to either DLRs or ONERAs or any other organization. So it is just an example showing that aviation is complex and we need to collaborate together to do research on sustainable aviation. So as you could see from the slide, so we have an aircraft designed with ONERA's FAST-OAD and INCAS, JAXA, and next SIA did aerostructure design. Next we have NRC. Now we go into a little bit more into detail, talking about battery management system. So Rasi, so the floor is yours.
Okay, hi everyone. My name is Faiza Rasi. I'm from National Research Council of Canada. Just a brief overview about what is going to be done in aerospace research and technology in aerospace. You can see in top boxes, and they are including autonomous aerial mobility, sustainable aviation, and digital twins and certification, air travel research, defense and sustainment, icing and safety, aerospace manufacturing and automation, and also climate resilience and space. So I'm from gas turbine lab, which is one of the 5th department of aerospace center. And my group is named Zero Carbon Team. And my discipline and background is mainly about aerodynamic and heat transfer. And most of the work that I've done so far at NRC relates to hybrid electric aircraft. And it's mainly about a thermal management system, as well as the boundary layer ingestion, which is a hot topic these days about new configuration of aircraft. So the contribution of NRC for this cool IFAR challenge was about thermal management system. So what is thermal management system mean? So it is the part that controls the temperature of different parts of the aircraft. And it would be from like engine, hydraulics, flight controls. Also, it can be like, it's not always removing heat, but sometimes we should add heat in some parts, like anti-icing surfaces. Also, providing some thermal comfort for cabin is also part of the thermal management system. And the main part is electronic devices. So it is most important for hybrid electric and fully electric aircraft. But for this specific challenge, we didn't have that like electric part. So then it would be just for a small part of the electric devices. So what's the source of heat on this type of aircraft? So it could be either internal or external. So internal, as mentioned, it can be from like engine, electric parts, and also cabin. So it's from like body metabolism also can create heat. So this is why we need to also make the air condition well there. And also external heat source would be from like surrounding environment. And the requirements to do the design and analysis of thermal management system are including having the system and weight breakdown. And then we need to find what is the heat loads. So what would be the resources for sources and sinks in the aircraft? Or for example, what would be the proper coolant for this system? And also temperature levels of different parts, and also efficiency of the engine and different electric parts is also very important. And then the mission of the aircraft, what would be the flight phases, because we need to estimate this for all flight phases. And then what would be the limiting factor? For example, about the safety, or do we have enough area to install this thermal management system, and what would be the size of that? So having all this, we can do some system analysis to find the best cooling capacity, and then after estimating one design, we can improve that design based on all these factors that's mentioned here. So main things that needs to be taken in mind is considering the weight, which is very important, and also power consumption, and also aerodynamic dynamic. So all these have been considered in this challenge. So the inputs came from ONERA, which would be about the flight profile and the power of different phases, and what would be the efficiency of engine for that. Because the main source of heat for this aircraft challenge was engine, of course. And also the output from my work was about efficient thermal management system. And so you can see in this picture that it's considered to add the thermal management system on top of the nozzle. But again, here we're gonna have some disadvantages, because it's gonna affect the, disrupt the airflow, also can maybe decrease the thrust, or create some drag. So then doing some optimization, we can decrease all these bad effects. And just, I'm not going to details of my calculation here, but I'm just roughly saying that one, like a TMS system, which is heat exchanger, you can see in this picture, was selected based on considering the coolant at jet fuel and like other parameters of the air. The efficiency of the heat exchanger estimated to be 99%, but it is highly depends on the temperature of air as well as the temperature of the coolant. So if you can see on the right-hand side, there's a plot that shows what's the relation between the heat transfer from this heat exchanger and the temperature. So as we have higher delta temperature, we're gonna dissipate more heat from heat exchanger, and it's more useful. But if not, then we're gonna have challenges. So based on what I mentioned about these different flight phases, we can estimate what is the heat losses. Then comparing the heat loss with this heat transfer, if we have heat loss less than dissipation heat from thermal management system, we are good. If not, we need to go and modify the system again. So that's pretty much about my work.
Well, thanks again, Razi. As you can see, there's more than aerodynamics and structures to design an aircraft, right? What did you study?
Aerodynamics. So aerospace engineering was my bachelor, and then after that, aerodynamics.
Okay. Ibrahim, are you happy to send her here? Okay.
Yeah, it was actually a great opportunity to work at NRC and with these very cool guys.
Okay, thank you very much.
Thank you.
Thanks a lot.
Thank you.
Thank you, Rasi. So as I said, so we don't do all the organization, but also there were many, many tools. It is just a glimpse of what we did. We went deeper, we went broader and everything. As you see, it's like a symphony. So there are several tools and we need to work together. And so the inputs and outputs flow between different organizations. So what do we do next? So we want to work on more complex design and more futuristic design. And we all are from IFAR is a research organization forum. So it's International Forum for Aviation Research. We are researchers. We want to take up bigger challenges. And then there will be more challenges towards sustainable aviation aircraft. And also, as you could see, aviation is, as everybody mentioned here, it's very complex. As one organization, we cannot solve this. We need multiple organizations coming together. What better than starting when we are very young? So that's the whole challenge. This challenge was organized, IFAR organizes it every year, and Ibrahim and Bruno supported this time. And many thanks to Onera, which supported quite a lot to organize this ECA and to come make everybody come here, like 18 countries coming at one time during Paris Air Show. It's hard to come from city to here. So we all came from different locations. So that's a good challenge. But towards future, what we want to do is go in 2023, we have a baseline. And after this, we want to continue towards the future aircraft, as you could see. With this, I end my presentation. Joe, over to you.
You end your presentation, but you're not at the end yet because we are here, obviously, in a room where there's a lot of talk about energies and SAFs and whatever. But obviously, we also need to change the aircraft at some point in time, right? So what is the final goal of this IFAR exercise?
Yeah. The first one we are doing is we calibrate ourselves. We come with all the researchers. The final goal is, example, like US has, NASA has N+1, 2, 3. Europe has Flight Path 2050 goal. So we want to have a sustainable aircraft. Sustainable means what? It means in terms of fuel efficiency, in terms of economics, in terms of operations and everything. So we want to have a carbon neutral and sustainable aircraft going forward from here. As you could see, these are the research platform developed by several organizations. And then there is much more. And we want to go towards the zero emission aircraft. Yeah.
Okay, thank you. As we have our next summit in October, and of course these two heads of establishment are the main partners, the main principals there. Could you say a few words if you support this activity? Of course you do in the past, but the importance maybe of bringing people together. I surprised them. Okay, so
it's okay. Yeah, I mean, you know, innovation, discovery, you know, the things that enable us to reach beyond our grasp require human innovation, and I think that occurs when you get people together that have different backgrounds. Different education, different ways of thinking, enables new ideas to be created. So yeah, I think these kinds of activities are critical to that dynamic. I also think that, you know, as you know, this particular thing is with respect to early career, and I think there's a great opportunity both to establish that kind of dynamic early, establish it across cultures, and you know, and quite honestly, you know, in the early career phase is when you can perhaps think a bit more out of the box. You have that ability, that luxury, and hopefully you're your bosses are pushing you to think a little bit out of the box, right? Because this is the time to do it. So I think all of that comes together to enhance innovation and to enhance idea creation.
That was well said, Bob. But I'll just add my my 2 cents on. You know, you heard about the 2050 goals that requires a lot more innovation in many areas. The sustainable aviation fuel is one of them, but there is the improvements in the technology, the air traffic management system, all of that. You know, by 2050, I'm probably retired. I can safely say that. But I think the future of solving those challenges with that time scale depends really entirely on the youngsters. It is very important that you establish that links, and the X challenge really actually connects people with their own expertise. It's not sort of connecting people in a conference type environment, building sort of social links. It is actually connecting you with your expertise. It's actually providing them the opportunity to be complementary. That has that added leveraging value. So I honestly think not only it excites the youngsters with challenging problems, but the problems themselves are significant enough that, and it takes such a long timeline. I think it's very important to do this kind of activity on an ongoing basis.
Okay, well, thank you. Well said. And what you said, please bear in mind, stay curious, you know, maybe look at other areas as well, as long as you can. This is, you know, if you rise up in the hierarchy, you lose maybe also that ability to look around. And specifically in this international and intercultural environment, I think you can learn a lot from other nations. And maybe, Bob, you talked about your innovation ecosystem. It might be part of that. I mean, it's outside the US, but still you get an influence if you send a lot of people also to the next ECN. That actually was my little talk. Okay, well, are there any questions from the audience while we have these gentlemen here? I actually mentioned to present you some other ECNs and where they come from, South Africa, for instance, but because of the time, we skipped that for the moment. What I could add in the end is that we have our General Secretary here from the German Aerospace Center. She has a few brochures and things like that if you want to learn more about IFA and more about the ECN and what we are doing. And I think I really enjoyed that talk. Please thank the 3 young ECNs who came here on stage and present their work. I think that was really great. And of course also to Prajwal, who is at the moment leading that, but as he is, I mean, also he is getting older, right? So he will give that into other hands. And thank you, Prajwal, for organizing all that. I thank you 2 guys for staying with us. You had a comfortable seat compared to down there, right? So you cannot complain. And again, a lot of thanks to Honora, who made all that possible, to our incoming chairman, Bruno Saint-Jean. Thanks a lot, Bruno, for making it happen, all here at the Paris Air Show. Thank you very much. And I hand back to the moderator.
Thank you very much, Mr. Södrich, for this insight into AFAR. I just wanted to tell you that we have another meeting at 4 p.m. if you want to be here again. We're going to have a very interesting roundtable between 2 builders. One builds airplanes, the other builds terrestrial buildings. And the first one is the chief architect of the Airbus company. So we will have Mr. De Zotti here, the chief architect of the Airbus company, at 4 p.m. And he will meet with another architect. It's going to be very interesting to see how they talk together, and they're going to talk about sustainability, of course, and autonomous capabilities as well. Thank you very much, and we'll see you at 4 p.m.